Thank you to the organizer for the invitation. Now we'll talk about the architectural interaction of faults within a particular rift segment of Northern Apennine. That is a result of part of my PhD project. So first, a few introductory words about the Apennine for those who may not be familiar with it. So Apennine is a classical region where investigating active extensional tectonics. It's a slow deforming region characterized by a long-lived contractional belt, which migrate eastward over time to a chain scale anticlockwise rotation. And shortening is then followed by coeval extension, which migrate with the same rotation and progressively overprints the truss belt. Because extension rate increases along the chain to the south, the result is a triangular-shaped back arc rift system. So the continuous migration of extension produces a series of morphostructural domains that experience different amount of extension over time up to the semi-transposition of early contractional feature. So from the west, we have the Tyrrhenian Sea, that is an overextended domain, then follows the truss belt domain, a transitional belt, where switching between contraction and extension is now occurring, and then the active contractional belt and the foreland at the east. In Apennine, what's happening at depth is highly debated, and rifting is believed to be driven by a combination of Adrias-Labrador back, orogenic collapse mixed with some rotation, which is well simulated in this model here. And the differential widening of the extension of the rift is linked to prominent lateral steps that occur at all the scales, from regional morphostructures such as echelon basins to individual fault system. And these steps have long been associated with transverse lineaments up to orthogonal to the chain, and have been interpreted in different ways, such as transverse zones or upward migrating slab tier faults from the basement and from the slab. However, they are rarely being observed at the surface, so their origin, style, and their seismic potential is largely unclear now. And the echelon structure of the rift is particularly evident in the arrangement of basin at its narrower northwest tip, where historical and instrumental seismicity is concentrated along a high topography region that is near the orographic divide. Most extension is attributed to rift parallel fault, that is traditionally considered the main seismogenic structures, with event exceeding magnitude 6. And however, the pronounced stepping suggests an underestimated role of transverse deformation. So if you zoom in a little further, we observe that the stepping pattern also exists in the orographic divide, and across the divide, the extensional faults are differently arranged. In fact, the divide separates an internal domain with long and hard link the rift and transverse faults from an external one marked by highly segmented curved fault with poor expressed transverse faults. Santana area is particularly interesting as a major fault curvature aligned with the northeast prosecution of transverse segment. And more, because in 2013, a deep magnitude 4.8 event occurred here. It was followed by a dense aftershock sequence. And its focal mechanism from the National Institute shows push-track slip motion. And nevertheless, the geological database do not report any faults that could explain the observed seismicity. So all these features motivated our interest of this area, which is ideal for studying transverse tectonics. In particular, understand how much the stepping can be due to transverse structures and how extensional basing initiate and link across their lateral step. So we first followed a seismological approach aiming to create a high-resolution catalog of earthquakes and faults. And we start with the absolute nonlinear location of earthquakes with nonlinear lock using a local 1D velocity model and the INGV catalog P&S wave arrival times from the earthquakes covering the period 2006-2023. And we then refine the event clustering to double different relocation using IPODD and catalog differential arrival times. For major event, then we manually pick the P-wave polarities and constrain the focal mechanism with FOCMEC. And we then model the 3D fault planes graphically using Okada standards and use them to simulate transfer of stress after the 2013 main shock. Then we finally used a field-based structural approach to strain the palus-strike conditions of exposed transverse structures. So we analyzed 5 sequences. Here are shown in the time series, each corresponding to individual clusters. So the major ones are occurred in 2013, 18, and 22 with a similar earthquake depth range. Here our catalog can compare with the original INGV1. So we can observe that after the hypo-DD clustering improved a lot, also with a significant statistical improvement of the location. And so we use this catalog for further analysis. Here the earthquakes depth distribution. So we see that the seismicity is deep, with most events occurring at high depths and placing the 2013 main shock near the maximum recorded event depth. So here the seismic cluster are color-coded by sequences in both map and cross-section, and the corresponding faults are summarizing this sketch here. Seismicity broadly migrate across the cluster to the east over time, starting with the 2006 one, which is in yellow, and which aligns along a minor high angle east-west fault deep into the north. Then we have the 2009 in purple, which locates on a medium angle southwest dipping fault. The 2013 aftershock in green and locates on a 8 kilometers long rift fault, which is an F2 in the figure, deep into the southwest down to 18 kilometers. And this cluster aligns with the Fola fault, which is a master fault surfacing to the northeast, and there's a remarkable morphostructural evidence with 2 kilometers of throw and bounce the Sant'Anna area in a young half-graben. And finally, 2018 and 22 in blue and light blue, which locate on narrow east-west oriented fault, steeply deep into the north, and located at the footwall of the previous faults. So we confirmed the INGV strike slip solution for the 2013 main shock, while all other faults exhibit almost pure deep slip motion, with nodal planes well aligned with the cluster trends. Regarding then the main shock focal mechanism, it's we consider unlikely the scenario of left lateral slip at depth on a vertical rift-oriented fault. So we propose the existence of a dextral transverse segment at the base of the seismogenic crust, which is TF1 in the figure, and this corresponds to the northeast-oriented nodal plane. So for the main sequences, the main sequence, we suggest these two separate deep strike slip at TF1 and a shallower deep slip NF2. Another major transverse plane can be then inferred, which is TF2 in the figure, as it envelops all the eastern tips of the main clusters. This fault aligns with the abrupt decrease in seismicity, and it's shallowing toward the southeast, and it runs parallel to the near-surface transverse Sant'Anna fault. And finally, coincide with the location of two major historical deep earthquakes. So this fault work for sure as a seismic boundary, and the Sant'Anna fault likely represents its surface expression. Yes, these then are the fitted planes map view, which we use to evaluate whether the inferred strike slip fault TF1 could trigger the 2013 aftershock on the shallower deep slip Fola fault. So in this scenario, the receiver fault are oriented as the Fola fault, and the source fault is modeled as a transverse fault TF1, of which we estimated the rupture surface area in 2 square kilometers using some standard scaling relationships. And the results are shown here in the horizontal deep cross-section and vertical cross-section. So red areas represent positive stress changes, which promote the slip on the receiver fault, and blue areas where slip is inhibited. Most of the seismicity aligns with the positive stress lobes, where the stress is predicted to have increased. And so we can observe a strong correlation that strengthens the existence of TF1 and the stress-Stegen relationship with the Fola fault on top of it. We tried then to correlate our finding with a significant transfer fault system to the southwest, which is the Isola Santa Silico fault. It's a fault that exhumed in carbonates on the west boundary of the Garfagnana basin. In the middle of the basin, this fault capped the quaternary deposits, so revealing recent activity, and then it progressively disappears before approaching the orographic divide. So I made some field work in its internal portion, finding a complex system of transverse corridor of strike slip to deep slip deformation on multiple trends. and took a strain in which stress condition it possibly originate, and it evolved. I collect some brittle geometric kinematic data, and here are just a few examples. And it's very frequent to observe the situation of figure F with deep sleep and stress sleep indicators on the same fault plane, and overlapping without unequivocal relations. And this indicates intermittent switching of behavior. So here on the right, a sketch to summarize the geometric relations. And the major faults are northeast oriented and have dominant dextral motion, while minor synthetic faults are east-west and show left lateral slip. This is then the resulting tensor of the pulse stress, which are calculated for the stress slip transverse system and also for the normal rift system. And so these structural data likely integrate well with the seismological data, showing a similar sigma-1 orientation with respect to that of the 2013 main shock. And we believe that it's likely that TF1 and TF2 are connected to the northeast, the deep subsurface prosecution of the default system, which is buried and not fully expressed across the divide, so in the Sant'Anna Pelago area. Also to note
Simone,
that
you're now at 10 minutes.
Okay, thank you. So we also have to note that the multiple splay arrangement of the system is common in both the exhumed and the deeper environment in the area. Now, just a small step back to the contractional architecture. This is schematically how units are stacked in the region, and this stacking, of course, through the sequential incorporation of continental units beneath an advancing arc, which is characterized by episode of out of sequences, thrusting and front of folding. So shortening also accommodates to highly oblique ramps that allows the lateral transfer between the transsheet. And northeast of the Sant'Anna area, there's one of these major lateral ramp. Here I put a sketch to better visualize where the ramp locates. And this locates on the western flank of a continental truss sheets that have advanced laterally for several kilometers. So we can see that both Isola Santa Silico fault and the Sant'Anna fault align currently with this major lateral ramp. And thus we interpreted that they are the extensional angle expression of some persistent transverse deformation zone that is active in contraction. And these are ramps act as weak anisotropies, where late high-angle faults nucleate and superimpose on. And this generates at the survey the regional curved trends that we have observed yearly in the transitional domain. So since these structural nucleate from the lower parts of the units, we believe they originate from reactivating orogenic Mesozoic or basement structures. So to conclude, in the Sant'Anna area, we document a systematic pattern of active faulting near the extensional front with multiple coeval deep root transverse and shallow normal faults that operate as a single integrated tectonic system. And this is a summary sketch that shows how deformation and seismicity possibly transfer across a young step with the progressive activation of discrete small structures with different orientation and kinematics. And we observed that seismicity stopped on lateral boundary TF2, which is a major evolved structure up to the surface. And TF1, on the contrary, seems to represent an early stage structure still sitting in the basement, despite it has, again, a strong orthogonal trend. And both are possibly part of a singular early stage transfer zone. So we propose Sant'Anna area as an immature translational soft linkage zone where high-angle faults are beginning to reprint the inherited contractional structures on the way to establish a strong structural connection between the deep-seated structure and topography. So to gain the mature linkage between the offset domains, most reefs need some time. And Sant'Anna show clearly that in the first moment, lateral deformation have to be partitioned somehow within a complex high-angle fault architecture. So just a few broader observations, because in most rifts, such faults oriented highly oblique to extension start to develop only in a late rift stage near the seafloor spreading, with the oceanic transport faults being the classical example. And this is well shown in the recent analog and numerical models. So the Apennine, however, stands as a notable exception, since this observable orthogonal strike slip fault initiated very earliest during the extension, during the rift, thanks to the pre-existing infrastructure that already exists. So we propose that the Apennine provides a unique setting for understanding how pre-existing transverse fault can evolve and persist through an orogenic history, from the foreland to the thrust belt and into the rift at various stages of extension, up to sort of continental proto-transformed fault. And these all happen probably using persistent structural weaknesses within the pre-orogenic crust, combined with the structural features acquired during subduction itself. So I concluded. So thank you all for attending.
Awesome. Thank you very much, Simone. That was a beautiful talk and really beautiful work. I have many exciting questions because I'm really excited by your results, but I'll let other people ask questions, but I'll give you one. Yeah, you talked a lot about, well, I'll try to. Pardon me. So there's this fault that you named the Fola fault.
Yeah.
That's my name.
Yeah.
It happens to be my name. Is there a particular reason why it was called Fola? Is there a particular reason why it was called Fola? Is it some Italian name or?
Yeah, it's a toponymy of
I see.
It's a place here where the Fola originates.
That's interesting. Okay, now I have to visit that place.
Name of the place, yeah.
All right, also a question. So I noticed the Santana fault is orthogonal to the overall trend of the other normal faults, but it's still indicated it to be a normal fault, and yet it's parallel to the shear zone or strike slip fault that you delineated across the region. Okay. Is that fault? Sorry.
Yeah.
So is that fault active today, or was it just a fault that initiated a long time ago and it's no more active as a normal fault today due to strain reorientation, or what? Is it active as a normal fault today, being orthogonal to the other trends?
Actually, we don't know really. Okay. We have only some indication in the geological maps of the normal motion, because the displacement shows poor normal motion. But it's not so clear because the fault architecture there is very complex, so we don't know how laterally is accommodated the formation. And we are in a foreland environment, so the rocks are not they not register deformation very well.
I understand. Sounds great.
It's difficult to understand what's the activity of the fault. Probably it's both, as in the internal part, where the transverse faults are sometimes normal and sometimes dextral, and this happens with intermittent motion. And yeah, we are in transtension, so it's probably both. We don't know.
All right. Sorry. Thank you. No problem. I'll let others ask questions. So Sasha has a question and Mike has a question. Sasha, go for it.
Yeah, I missed in the introduction, probably you mentioned it, but how many of these current faults do you have to the north and to the south of the area? When you say in the end that there is some inheritance that's governing it, then I'm curious about how much inheritance you have in the other places along strike of the Apennines.
All Apennines. Across all Apennines.
Yes, you have them everywhere. These like transcurrent faults.
It's a long debated argument. In the north, respect to Meara, there are proofs that they are reactivated inherited basement structures. If you go to the south, there are a lot of works that talk about inherited Mesozoic or pre-Mesozoic faults. But the problem is there are few constraints, really few structural constraints of the possibility of that, because the basement only outcrops in some areas, and it's difficult because of the non-cylindrical architecture of the chain to establish if they are real inherited structure or not. We have very little geophysical proofs about that. So it's difficult in Apennine to establish this. And I think we need to do a lot of work to investigate more this problem of inheritance.